Alright, so now let's talk about, before talking about Stokes' theorem, we need to introduce the notion of surface integral. So I want to tell you in advance before I forgot, this video is pretty much related to the former video that you will see in the list in YouTube, surface area. So we are not only computing surface area of parametric surfaces, but we integrate functions which are defined over those surfaces. So what it's all about? Let's take you take a surface which is defined parametrically in R3, so parameterized by two variables uv, and at a coordinate uv you assign a three-dimensional point in R3. So if you let u and v, let's say, belong to a domain, what you obtain is typically a surface, yes. Well, what we will need to make sure is that we don't have, let's say, what we call singularities. We will not want to have, let's say, partial derivative of r with respect to u and partial derivative of r with respect to v to be collinear. Otherwise, we have a singular manifold. So this thing we want to avoid this quantity to be equal to 0. Remember, when we want to compute the total area of the surface, what we need to do is to simply compute the sum over the entire surface of the function 1 ds, where ds is nothing else than this quantity, this. I'm just reminding you what is the du. So pretty much like when we, let's say, when we look at let's say the measure of an interval, we say, well, what is the measure of the interval AB? We integrate dx between A and B, and then of course it gives you the size of the interval, nothing else. Then after that you say, well, we can also, we could give a different weight from A to B, and then you have a function f of x which is multiplied by dx, and we add those infinitesimal sums, or those Riemann sum, and then you consider the integral from A to B of f of x dx. This, I'm going to say exactly the same thing. What is a surface integral? You have a function which is defined above this guy. So for an element ds, I multiply this elementary surface area by f, by the scalar f of x, y, z, and I had all those infinitesimal objects above each point x, y, z, and I obtain these things. I will sum over the range of this parameterization, that is my surface, right? The scalar function f multiplied by this infinitesimal quantity, this infinitesimal area, which just tell me, what is the, when I consider an infinitesimal change of u and an infinitesimal change on v, what sort of area do I generate? Remember, everything is explained here in video, at least in heuristic point of view. Now I could say that actually that what I've written here is just a consequence of the change of variable, but it's also the way we parameterize the surface. If the surface is parameterized by r uv, I will therefore integrate over the domain D of f composed with r uv, and the ds is nothing else than this thing, and that's what we call a surface integral. So I'd like to discuss with you as an illustrative example, example number 1, which is completely treated in the book, but I like to discuss it with you also. I don't think it's a waste of time. So we are considering a parameterization of the unit sphere centered at the origin, and we want to measure the surface integral of the function f of x, y, z equal x squared. So let me rewrite everything. So I erase the formula that we will need to remember then. So example 1 again. Alright, so as I said, example 1 treat the case of a surface integral over the unit ball. So we are asked to compute this. So let's parameterize now the unit ball. Well, to parameterize the unit ball, the best way is to use, again, spherical coordinate. So x is equal to rho sinus phi cosinus theta, but where rho is equal to 1. So we could just have sinus phi cosinus theta, where phi here belongs to the interval pi and 0, and theta varies between 2 pi and 0. So let me briefly remind you that this is the picture we have in mind. The distance between the origin and this point is always equal to 1. This is the angle phi. And the projection of this point leads to a point which is here, and making an angle with the x variable, which is theta. So actually, take it back. The orientation of phi is not like this, but is positively oriented like that. Now y is equal to sinus phi again, but sinus theta this time, and then now z was going to be cosinus phi. All right. So this being said, I need to differentiate the position point with respect to phi, and then respect to theta. What do we do? dr over d phi equal cosinus phi cosinus theta cosinus phi sinus theta, and minus sinus phi. That's easy for this part. Now we need to compute the partial derivative of r with respect to theta this time. So I put them in that way, in such a way that after that I will be able to compute the cross product, and I will put it here. So differentiating with respect to theta, we got minus sinus phi sinus theta, then sinus phi cosinus theta, and finally 0. All right, so now let me erase where? I'm going to erase here, and I put the result here. It's not extremely nicely conventional, it doesn't matter. Let's compute first of all the last component. It's going to be the most delicate one, because I need to compute the determinant of this, but you'll see a lot of things simplify. We're gonna get sinus phi cosinus phi times cosinus square. So sinus phi cosinus square plus cosinus phi sinus square of theta. So you have a sinus square theta plus cosinus square theta times sinus phi cosinus phi. Well, this is the only thing that remains is cosinus phi sinus phi, because sinus phi, I said, cosinus phi sinus phi, because sinus square theta plus cosinus square theta equal 1. So that component was supposedly quite complicated. It's not. Let's compute the first one, which is mean I'm going to take the determinant of this guy. 0 minus this thing give me sinus square theta, sinus square phi, sorry, cosinus theta. And the one in the middle, finally, is going to be obtained by looking at the determinant of this guy, but by flipping the sign. So I gotta get minus times this one, which is sinus square sinus phi. Sinus theta, sorry. Alright, so now I need to compute the norm of this vector. So it could be quite scary computation, because I would have to take the square of this plus the square of this and the square of this and see what it gets. But as you will see, a lot of things simplify quite nicely. So this is nothing else. So this is R. So this is nothing else than dr of the d phi cross dr of the d theta in that order. And we need to compute now the norm of this thing. So this is equal to, so I'm going to take the sum of the square of those components and take the roots eventually. So we're going to get sinus 4 cosinus square plus sinus square. We get sinus 4 in factor of the sum of cosinus square and sinus square. That's going to give me sinus 4 of phi. plus cosinus phi square sinus phi square. And of course I need to take the roots of this. So here inside the roots we can factorize by sinus square to get sinus square of phi plus cosinus square of phi. Well, this you I'm quite sure you understand that the only formula I'm really using, trigonometric formula I'm really using, which is relevant here, is sinus square plus cosinus square of the same input. This is equal to 1, so the final result is sinus phi, which is good. It makes my life a little bit easier. Alright, so now I will be able to compute x squared. So this is ds, in other words. So ds will be sinus phi times d phi d theta, or d theta d phi, depending upon which is the order on which I want to integrate this. Alright, so this is the only thing I need to remember. A lot of work for pretty much almost nothing. So this guy will be simply like this. This is the sum over the rectangle 0 phi 0 pi cross 0 2 pi. So I don't know yet how I'm going to set up the iterated integral, but this is what it takes when I integrate globally. The x square, x is just the square of this, sinus square phi, cosinus square theta, multiply by the ds, which is sinus phi, so I've got a third here. So I will say dA of d phi d theta. Does it really matter in which order I'm going to integrate them? Not at all, because you have again a product of two functions which are completely independent. So you can say, I mean, the question was asked actually after quiz 5. Can we do this? Yes, you can always say that the product of the integral is the integral of the product if the function that you integrate is really the product of two independent functions. Otherwise, if they are not independent, and you integrate, of course, or the rectangle, otherwise, that doesn't make any sense. So this is the sum from 0 to pi of sinus third of phi d phi times the sum from 0 to pi of cosinus square theta d theta. Well, after that, I'm sure you guys can end up with the rest of the computation easily. Let's compute the first one. So let me change the color. Sum from 0 to pi of sinus third. I'm going to say that this is going to be sinus square of phi. What am I saying here? No, this is going to be 1 minus cosinus square of phi. That is sinus square of phi. I hope you all agree with me. And then I need to multiply by sinus t again. That's the trick that you guys have learned from calculus 2. And so that guy is nothing else than the sum. If I make a change of variable cosinus phi equal u, I got an integral from u equal 1 to minus 1 of 1 minus u squared. Sinus phi is minus du. So I write it like this. And this is, of course, easy to integrate. This is u minus u third divided by 3 taken between minus 1 and 1. So this is 1 minus 1 third twice. That makes 4 third, if I'm correct. 1 minus 1 third, yes, that's it. You could always say that this is twice the sum from 0 to 1 of 1 minus u squared, because 1 minus u squared is a even function. So that's right. And then we need to compute the sum from 0 to pi of cosinus squared d theta. Well, cosinus square theta, remember this is the half angle formula. It says it's 1 plus cosinus 2 theta divided by 2. And that guy here, the sum from 0 to pi of cosinus square theta d theta, is nothing else than the sum 1/2 d theta from 0 to 2 pi plus 1/2 times the sum from 0 to 2 pi of cosinus of 2 theta d theta, not dx. What do we have here? This guy is 0. Yeah, because it's a periodic function, and entire derivative of cosinus 2 theta is sinus 2 theta taken between 0 and 2 pi gives you 0. So the only contribution from this integral, and it has to be not trivial because you integrate it strictly, but it's a positive function, is just given 2 pi times 1/2. So the final answer is 4 divided by 3 times pi. 4 pi divided by 3, and that's the final answer that we, of course, retrieve in the book in the same way. Alright, so if you understand this example, you understand, let's say in theory, all the example. The only thing that you have to do, I want quickly to repeat what is the surface integral. Right. You have let me write it like this. You have parameterized your surface over a box in R2, depending upon U and V. And I call the parameterization R. You have a function f depending upon 3 variables, x, y, z. And you have this ds element, which is just the elementary area on your surface. This is nothing else than computing the integral over the box in the two-dimensional setting of f composed with R of u and v time ds, where ds is nothing else than dr over du cross dr over dv in norm dA uv. So depending upon, again, the way you're going to set up your integral, du, dv, or dv, du, that's your choice. But this is the only formula you need to remember. Now, this being said, we will be able to state Stokes' theorem in the forthcoming video.